All right, welcome everyone to the final presentations for the AI for Forest Elephants Challenge. Very excited for you all to be here. We have some very cool results to show you all. But I'll firstly give you a short introduction of who we are as Fruit Bunch and what we do as an organization and why we're building this community. So first of all, I want to thank all our partners who have helped us organize this challenge, but most of all, Daniela from Cornell University, who's running the Elephant Listening Project, for providing us with the data and the domain knowledge to get started with this challenge. So for today, I'll give you guys a short introduction of the problem that we faced and the challenge, how we set it up. And then you will hear from 4 teams about model exploration, efficient data processing, machine learning application, and model deployment to finally get all our models working on edge devices. Finally, we'll close off and we'll give Daniela some final words to thank the participants, and we can round up the challenge. So, who are we? We are Fruit Punch AI, and we are building the global AI for good community. And we do this because we believe that to solve humanity's greatest challenges, we need to educate AI engineers at scale and with an ethical and sustainable mindset. The way we do this is by organizing AI for good challenges that focus on one of the sustainable development goals. So we organize challenges in wildlife, but we also do it in sustainable energy, sustainable transportation, you name it, anything you can link to the sustainable development goals, we organize challenges in. We do this because we think that in order to actually apply AI in practice, you need to educate yourself in a challenge-based manner. And how to do this best then in a peer-to-peer fashion with people from the field who have already all the experience that you want to learn from. For this challenge, we had 10 weeks and we formed 4 groups. In total, 35 AI for Good engineers finished the challenge, and combined, that's an effort of more than 28,000 hours of engineering. So quite a lot of effort went into this challenge. And yeah, I think I can already say that we came up with some pretty cool results. So hope you're all getting very curious right now. The goal we set out to complete was optimize elephant and gunshot detection models to implement them on edge. So the problem researchers are facing right now is that they set out audio recording devices throughout the woods in Central Africa, and they go pick up those devices once every 3 months. So once every 3 months, they have around 50 of those devices located throughout the Central African forest. So every 3 months, there is a big load of data coming in. These are continuous recording of 24 hours. So you have 90 days of times 50. So that's like terabytes of data that's coming in. In order to process this data and to get good insights on what's happening on these grounds, we need to use AI to automate the gunshot and elephant detection, as well as to process this data as efficient as possible. We also experimented with some on-edge implementations together with some of the hardware we were sponsored by NXP. And we tried out to deploy these models so to see if in a further iteration of this project, we might be able to do some real-time detection of elephants and gunshots in the forest, because that's the ultimate goal. But for this challenge, the scope was to create AI models to detect these gunshots and elephants, but also to do this as efficient as possible to help the researchers from Cornell University, as well as the rangers going out in these forests to gather the data and to help them detect poachers and gunshots. We started this challenge on the 21st of February, and today on the 1st of May, we have the final presentations. Next week, all the teams will be delivering all their well-documented code and their report to the researchers at Cornell, so that they can use it in their research, as well as to implement the results in their work. So I won't want to take up too much of the time, and I want to give the floor to the model exploration team.
Cool. Okay. I'm from the model exploration team, and together with Patrick, Emil, Traun, and Carl, we looked into the new models. So what we did during this What I will be talking about is the goal of this of our team, the solution direction we went into, and the struggles. Then we go over the models and the results, the lesson learned, and we also finish with some future work. So the goal of our team was to explore different models for recognizing elephant rumbles and gunshots. The impact that we made is that we explored state-of-the-art models in sound event detection. We developed an easy-to-use pipeline to develop and evaluate new models on the existing data. And we trained 2 new models for rumble and gunshot detection in the jungle environments. And so first go over the solution. So the solution that we built was like the pipeline for pre-processing, training, and validation of the models. And the 2 models that we made were an audio spectrogram transformer and an hierarchical token semantic audio transformer. We specifically looked into transformer architectures because the previous work that was done was mainly based on recurrent neural networks. During this challenge, we had a few struggles. So it took a while to pre-process data because it was a struggle to get it into the right format, and also because like you get 24-hour clips of 24 hours, but in the total, 24 hours, not like most of the time there aren't any rumbles, so you have to extract them basically. This topic is pretty niche, so there are not real benchmarks in this case, and that also made it hard to find suitable models. So for example, there are no really sound event detection models on Hugging Face. There are some models for related problems, but not for this specific problem. So we ended up by adapting models from papers. So now I will talk about the models and the results. So first, I briefly say what sound event detection exactly is. So on the left part, you can see a MEL spectrogram of a clip. And beneath it, you can see an event matrix with the 2 classes that we were interested in. So we got the rumble class and the gunshot class. And the white part indicates where a rumble occurred in the clip. And basically, we want a model to predict this event. So the first model that we looked into was the AST model. I will briefly talk about like how this model works. So the first step in the AST model is to split a spectrogram into 9 parts, basically. Then we perform a linear projection to get embeddings. And then with self-attention, we apply self-attention to these embeddings to get hidden states. And then we use those hidden states to get a event matrix. And for each second, we produce 1 hidden state. So we can do a prediction for each hidden state to correspond to like 1 second. And Patrick is now going to talk about the other model and the results that we got.
So the another architecture that we tried out was the HTS-AT, which stands for Hierarchical Token Semantic Audio Transformer. It's in essence a pretty similar architecture to the AST. AST stands for the Audio Spectrogram Transformer, which is pretty much a vision transformer applied to spectrograms. And the HTS-AT is a swing transformer, which is a sort of evolution of a vision transformer. So we can also hear, I see the hand raised up. Okay, that was a mistake, I think. So it also is split into different patches that goes into the swing transformer, which, as we can see, gets narrower and narrower, which is the main difference between audio spectrogram and the HTS-AT, is that we look at different resolutions in the spectrogram at different parts of the network that gets reshaped into a latent space, which is fed into a CNN, which outputs the event presence map, which is also basically our heat map of probabilities of like class being in each time step. On the next slide, we can see yeah, like the main difference between the AST and HTS is that we look at the different resolutions. So if anyone wants to like get more into the technical details about these networks, then they're based on the vision transformer and swing transformer, which is basically just applied to spectrograms. On the next slide, you can see that we had to do a small adaptation of the network. So we deleted the last layers and used the event presence map, which is the heat map of class being at each time step, as the output, and use that as the predictions of the model to which we applied binary cross entropy. So for the results, we can see that, perhaps somewhat surprisingly, the HTS performs worsely, which will be explained in a second. So for both rhombus and gunshots, we achieved 94% accuracy, 0.89 F1 score, 0.88 precision, and 0.9 recall, which recall is pretty significant because low recall means that a lot of the clips need to be checked manually. And HTS is basically slightly worse on each of these metrics. So on rhombus alone, we can also see the comparison with the previously developed Stanford model, with which the transformers get slightly worse results, but they're not really comparable because the Stanford model was trained on different dataset, and also the evaluation was slightly different. But still, here we get pretty good results for the AST. Okay. On the next slide, we can see what an example output looks like. So it's basically a probability for each time step that either a gunshot or a rumble occurs. The 0 here is the rumble, 1 is a gunshot. And yeah, we can see that it looks pretty valid in here. Okay, I'll ask the questions in the chat later after that's done. So lessons learned. And then definitely having a good data pipeline early on is pretty crucial, because that helps you iterate over new models over and over again. Setting up deadlines for model research is something that we struggled quite a bit with, because we kept finding new data sets, new architectures, new papers. And we spent a lot of time like trying to decide which one to implement, but that doesn't really help. Like such a long research doesn't really help in a short project. So it's important to get your hands dirty with the project early on. It creates a lot of momentum, helps things going on. And it's important to think in terms of MVPs. So trying to basically deliver something SAP and then working on improving that. So for the conclusions, we have built our repository that's a good basis to build for the open. We have implemented 2 models, the AST, which is really fast, it's rather small, and it achieves pretty surprisingly good results. And the HTS, which is, if I remember correctly, 100 times bigger. It requires some additional work to adapt it to the smaller dataset that we have. And but it has more potential in it. So for the for the future work. So the framework for effective data processing and training the models is built, and we can add to it things like data augmentation, hyperparameter tuning is really important here, adding some labels, so if you want to detect more events. The HTS definitely needs regularization to adapt it to the smaller dataset, because we have a lot of audio, but once you extract just the events on short clips, then that becomes like less than 100 hours, which isn't really what HTS was designed for. So that we could also pre-train on older data, we could pre-train that as an autoencoder on the whole dataset, and then just fine-tune it just the events. And as always, you can add more data. Okay, so that's everything from our side. I saw some questions in the chat.
All right, thank you, Patrick. I'll read the questions. So the classifications, are they binary?
I mean, we're doing some event detection, so it's not really a binary classification because we're doing for multiple classes at multiple time steps.
Yeah, but I can add, in a way, there are binary, because for each label, for each time step, you decide if there is the event or not. So in that way, it is binary.
Yeah, okay. There's another question. Did you investigate secondary metrics as well? So how do these models compare in terms of number of parameters or interface latency, also against simpler models?
We didn't do that because we didn't have time for that. But especially latency is pretty important in this case, because they want to be able to run the models on edge. But just during like training, we noticed that at least AST is like pretty fast. So that's like hopeful.
Yeah, I can add that the AST is faster than the CRN developed by the Stanford previously.
Right. Final question. I don't believe you guys did any augmentation, but there's a question: what kind of augmentations can be used in this type of work?
I mean, what can be used? It's basically everything that can be used in standard audio processing, which there's quite a lot of data augmentations. We didn't really have time to like explore that a lot, but for example, in Bearded paper, there are a lot of like augmentations for bioacoustic event detection explained.
All right. So thank you, Team 1. Good presentation. Good work done. I think you've, especially with the whole pipeline that's built right now, you can easily explore other models as well. So great job on that. Thank you very much.
Perfect. This works. So hello, everyone. I'm Masoom from the Efficient Data Processing team. I want to start by a quick thank you to the Fruit Punch team for organizing this, giving us the opportunity, and also really good progress by model exploration team. I'm excited to try out their model with the pipeline finally to see how fast it is. So let's start. These are some of the topics we'll go through today. We'll meet the team, we'll discuss the goal. So this is the team. We're 7 folks. Couple of us are a bit camera shy. We're working on that. And so I'll quickly start with the goal. It's we wanted to build a pipeline to efficiently process the massive audio files we have and generate spectrograms to use them for generating predictions with the model exploration team gives us. As part of this goal, we kind of, we divided it into 4 sub goals that we can break and achieve. One was making data loading and files, making data loading file system agnostic and faster. So we saw in the current implementation, the way we were reading data was very much dependent on what kind of machine or OS you're using, what kind of file system it is. It was kind of dependent heavily on the paths and everything. We wanted to improve that. We wanted to make audio processing and spectrogram conversion faster by exploring different libraries. We also wanted to implement a better architecture for spectrogram processing and generating predictions. So here we are talking about the higher level architecture concepts of how the data pipeline should be made, how different parts of the code should work, should input and output data. And also last is we wanted to make outputs processing faster and easier for the model application team, and also make it more seamless for them to take the outputs from the model and do something with the GUI application. Can you jump to the next slide, Steve? Perfect. So as part of these, the whole process. It can be divided into these different steps. We started with a technical setup and onboarding with the team. We use GitLab and Amazon Studio Lab mainly. We researched the current implementation, identify slow processes, and then we implemented some of these things. And then now we're here reporting and presenting our findings. So the first step, can you go to the next slide? Thanks. Oh, the slide before. Yeah, perfect. So we started with finding a good profiler for our code. Because from what we understood, one of the major problems the application was facing was that it was taking a lot of time to process even a 24-hour audio file. And we would have many of these files. So a good profiler for Python code would help us figure out where some of the bottlenecks are in our code, where processes are slow. We found Scalene, which fit the best in this approach we wanted to take, mainly because it had a very less overhead. It's at max, in our experimentation at least, it's only at a max 5% slower when we use profiling. It's the only profiler to profile at line and function level. So we were able to pinpoint where the problems are and solve those. And also supports use of multiprocessing, which was one of the huge things in our implementation, because multiprocessing gained us really good advantage on speed. And also that it can break out Python versus native time code. We realized three main bottlenecks in our process. The slowest one of the entire process was the part of the code base which was fetching spectrograms and feeding it to the model to eventually run inferences on it. Also, the model itself was slow, and thanks to the model exploration team, now we have a faster model. And then the converting audio files to spectrograms was also a bit inefficient process that we could have improved upon. And so for starters, we use multiprocessing and concurrency to speed up the inferences generation part. The original estimated time was approximately 110 minutes on MacBook Pro 2019. It's a 6-core i7. So we were able to use multiprocessing. With 6 cores on Macs, you can get 12 different processors. So you get we were getting about 14 minutes of time to run inferences at max. This is the worst case time. We'll see what the best case time looks like in a minute. So this was one of the first things we implemented. It was pretty good. The next is, can you jump to the, yeah. Next, we researched on some audio.
Oh, sorry.
No worries. We researched on some audio processing libraries and made some improvements on the spectrogram generation part. And I think Estin will be best to take us through this implementation part. So,
Yes.
over to you.
Thanks, Masoom. Yes, so some of the research that we didn't pan out as we hoped initially. The audio streaming and the asynchronous programming part specifically, it was quite complicated to get the full pipeline running with it. Initially, we thought that we could start from scratch, do everything over, but then we realized that it's probably not the most feasible task to take on in 10 weeks with limited hours in a day. So the gains were also not that big with the asynchronous programming because the bottlenecks aren't the I/O operations. It's the CPU type computations that were taking the longest, and with asynchronous programming that won't be improved much. So we stuck to what we could do, which one of the things was loading and resampling these 24-hour files in a more efficient way. So those are just some of the benchmark files that we used. And according to the model exploration team, they used the 4 kilohertz sampling rate for training the models. So we we focused quite a lot on the fact that we would need to resample these massive files. So WAV file, for instance, it was quite short if we're looking at the input sampling rate is already what you want it to be. So for instance, if it's 4 kilohertz, then it loads quite fast for the whole file. It was actually, but it can't resample on its own. So you would have to use something like resampy to resample it. And you can see here, sorry, my mouse isn't working so well. So it takes about 570 seconds to resample that long audio file. So it gets impractical. And in the end, mini audio could be used, but I think that the best option was Labrosa, because if the resampling wasn't necessary, it was the quickest. But if it is necessary, then it's still almost it's comparable to these quick ones. So we stuck to Labrosa then in the end for resampling the files that would be necessary in the whole pipeline. So that, I guess, it added a bit of time, but it makes the application more usable for the researchers. And then on the spectrogram generation part, we also parallelized an aspect of it. So initially it took about almost 3 minutes, so roughly 160 seconds to generate a spectrogram for one 24-hour file. That's on my computer now, but it's also a 6-core i7 processor. And then when we parallelized it, there's almost a minute improvement. So that was brought down to less than 2 minutes. But Masum showed me a trick last night. I just haven't had time to implement it, so we'll get that even down further. I'll finish that up this week, and then I'll report back on the group what the final result is. And then, as Masum said, one of the problems that we wanted to address was to make it system agnostic. And one of the problems that Daniela and them also listed was that you always have to use a / and you can't use spaces and things in the directories that you pass to the old application, at least. And the reason for that was that they used literally the split function based on /. So we just took out those inconsistencies and used the join function that makes it system agnostic. So now you can use / /, /. Here's some examples. You can use things with spaces. If you use spaces, you must just remember the quotes. So I think that'll also help them with the usability aspect. And yeah, then the overall results that we achieved were bringing the processing time for one 24-hour file from about 1 hour and 15 minutes to roughly 16 minutes in the worst case. And Masum ran it once with 4 minutes in the best case. I'm not quite sure, what affects the processing, probably whatever you're doing in the background and things. But I mean, that's quite significant an improvement. And so with integrating the new model that we also believe is much more efficient, and that final part that I'll implement for the spectrogram generation, we expect the best case time to be roughly 1 minute per audio file. And yeah, we achieved to make it system agnostic, and we implemented some of the best practice architecture and data pipeline procedures that we researched, and we definitely gained a lot of new skills. And then some insights and recommendations for the future. And we actually didn't even replace the spectrogram generation function that they used in the old application. So there could be some improvement there. And I think if we also move to null spectrograms, or if the model exploration team's model needs something else, we can research how to do that in the most efficient manner. And then this next one is something we discussed in some of the meetings to see, what accuracy versus speed compromise there is if we lose the sliding window, because that will mean that you do inference on a lot less samples, basically. So that could definitely speed things up a lot if it's worth the sacrifice in accuracy. And then one thing we wanted to add, but we didn't get time yet, is that to improve the error handling, but also to log, so that they can see in the output results folder, something if a problem occurred, or where the problem was exactly, so that they know which files maybe to have a look if something is corrupted or whatever. And then we also obviously still need to integrate with the rest of the teams. We need to add stuff to use the new model and interface with a GUI application. And then, yeah, we also learn, I think, as Patrick also said, that the product owner role is critical, but, we need to think from the start, how to define and work towards a minimum viable product. And I think the best way that we found in the end was to rather make the existing application more efficient so that we can deliver something that they can definitely use instead of, starting with this big pipe dream and, not being able to reach our goals.
Very nice. So that's a five-time improvement from an hour and 15 minutes to 15 minutes. I guess I find that pretty impressive. I see there are some questions.
Just another comment. I think, Masum, you ran it on GPU once, right? And it was quite fast.
Yeah, on a GPU, the inference takes less than a minute. I already know with the model exploration team about 18 hours of audio file with I'm not sure how many number of frames, because I think they did not try sliding window approach, but it takes about 40 seconds for a 24-hour audio file, which means with these improvements and some improvement with the spectrogram generation part, the best case time can probably be about a minute or two, can be brought down to a minute or two, I think, on a CPU. But again, I'm not sure how good this mimics an actual machine in the actual use case we want to use it. But yeah, it's still, I would say, significant. Yeah.
Yeah, nice. So as it's working right now, if you have a GPU available, does it automatically switch to GPU or?
Yes, it does currently automatically switch to GPU. I just realized this morning that it doesn't even need to be CUDA supported only, because I have like 2 GPUs on my machine. None of them are CUDA supported, I think, but it still works. And the inference time is less than a minute. And so it will switch according to if we have a GPU or not.
Nice. Yeah, I think that's very valuable for Cornell as well. All right. Thank you. Yeah, so we'll pick up the integration with the application team and the model team. I think tomorrow somewhere I'll put it in Slack. But then we going to implement everything in the application. So thanks, guys. Good presentation. Very impressive work. And now we're still already talking about the application. I'm looking at Emil already. Yeah, you can have the floor for your presentation.
Thanks. Right. So once again, thank you, Daniela. Thank you, Fruit Punch, for hosting the challenge. I learned a lot. I think the rest of the team also did. And yeah, this was really cool. So yeah, model application. We want to integrate the parts that we just saw in one concrete user interface. So people in the field can use the model without too many bells and whistles, and it's just a click of a button to get inference results. So we worked on this. These are people who worked on this, and Sebas joined in, and Natasha also joined in halfway through the challenge, which was a blessing because the work wasn't really going forward that much in the first weeks. So it was really nice the past weeks to work on it together. So the problem is in the field, researchers need to be able to make predictions on new audio files that come in. And this needs to happen offline without internet usage on basic hardware, so CPUs, not necessarily access to GPUs. So for that, we need like an application that can work offline, of course, and that is intuitive, doesn't have too many things going on that distract you from the goal of the application, which is just running the model. Because in the end, Daniela and her team use Raven Pro software, which is analysis for audio, which they actually use for further analysis of these audio files, so spectrograms, analyzing events in audio files. So the goal of the application is kind of constrained to being able to run the model itself and get inference results efficiently. So yeah, and if we have that, it's very easy for everybody to use our software. what we built, and that's pretty cool, of course, if everybody can actually use it in practice. So yeah, we want an offline application. Simple, like I said, we decided on Python based, since everything else is also in Python that we wrote. And we need to make use of local file system. We don't use any database, no cloud usage, and we need to be able to meet all the requirements that an end user is asking for. So first we spent time on defining what needs to be in the model, or in the application, sorry. And like, so we have clear, this actually took a while, so we have clear what is being asked from us, what has priority, and what needs to go into the design of the interface, right? Then we actually designed initial wireframe and created an application in PySimple GUI. So this is a framework that allows you to like make very basic, or like, yeah, like from scratch, simple Python applications. And it's very straightforward to use, and you don't need, like I said, a database for it. So it's very convenient. And it's also, you can also wrap it in an executable, which makes it very easy to import onto anyone's local device. Yeah, in the end, we merged this with the pipeline of model exploration. So we actually have right now inference running using the models that we built in the past weeks, and integration with the efficient processing team still needs to happen, like I said, like they just told us. So yeah, in the midterm, we for those who were there, you probably remember we didn't have much progress due to lack of structure and not a clear vision for the application. But then luckily a change happened and we could actually put something concrete on paper, and we started working on application, and now we have a working MVP. So that's cool. And yeah, let's open the application, I'd say. Yeah, so as you can see, very simple interface. You click analyze, you can pick any audio file that you want, and it's possible to load in long files as well. So 24-hour files are loaded in very easily and analyzed easily as well at the moment. Just CPU, it doesn't use any GPU. So let's pick an example file. You get some statistics about the file, such as name, duration, sample rate, and then you get 2 fields for detections, for rumbles and gunshots. So that's basically, yeah, the core of what we want to see, of course, just analysis results. So you click analyze, and like this white thing here is a progress bar, but we need to set up a separate thread for running for the getting the analysis results to the front end. So right now you don't actually see it updated as it goes, but as you'll see in a second, it's going to be switched to green, which means it's done. But it's going to be incremented like throughout the analysis, so you actually see how much time is left when we deliver the next week. But right now it just shoots from 0 to 1. So that's, yeah. Okay, it should take around 20 seconds max for a 24-hour file to yeah, run inference on. So that's cool. Yeah, right. So now we get rumbles that are detected in like, yeah, in this long audio file, and gunshot as well. And right now, like, so for inference, we're using a threshold function, which says if a softmax is like higher than a certain value, we detect the label as an actual audio event. If not, then it's noise. So like we get quite a lot of detections, and this needs to be tweaked in the coming days. So in combination, like, yeah, like discussing together with exploration and processing teams, how we're going to do this in the best way. But basically, yeah, this determines which audio segments are actually interpreted as audio events. Yeah, so like it might be that some of these events are not actual audio events. I mean, to cut that down a bit. Yeah. But yeah, you see here a list of gunshots, list of rumbles that are detected within this audio file. And yeah, that's basically the core. You can remove files, you can add different files at the same time. So I only have one on my computer here, but you can get a list of different ones. And then you can also say remove all, analyze all, and export. And if you that's an export. So like exporting means detections are all converted to a data frame consisting of all the columns that we need for Raven Pro software. So selection IDs, time offsets, frequency bounds, which are like set to 0 and 20,000 right now. So not actual bounds on the frequency, but I think, yeah, out of discussion with Daniela, we got that we don't actually need those to let them in. So we just set them to the highest and lowest values that we need. So yeah, then you export the data frame and you get a CSV file out, which you can load into your analysis software later. Let's see. Yeah, so you would say export and this application, and then you would find somewhere. Let's see. Sorry for the messy file structure. Yeah, so you get this kind of like table with the file that is being analyzed for every event and beginning of end of every detection. So every audio event. Yeah, this is a dummy file because we have to make some tweaks in how the data frame is actually constructed, or like yeah, there's some like things in the backend that need to be fixed basically. So we actually get CSV files like that are like agnostic to the structure of the entire thing. So yeah, like in the end, it's going to be a bit more flexible. But yeah, that means that you get CSV files for any audio file that you have, any WAV file that you have. You get a CSV file out that gives you all of your predictions in a nice format. Yeah, which is the end goal of the application. But that's basically the functionality of the application as of now. And like I said, more integration is going to be included. But yeah, I think it's a nice. Oh, let's go back. It's pretty cool that we managed to get this MVP working, and yeah, it's relatively fast. It's surprisingly fast, which is a cool thing. So yeah, that's the demo. So yeah, what we learned is sometimes easier applications and interfaces are better than more complicated ones. At first, we wanted to go for like web-based, like radio or Streamlit, but then some people cannot use it if there's no internet access. So very simple framework and very simple structure. But everything works. Everything is kind of fast, and yeah, we also learned that we need a structure in our team, and like we just heard as well, like good team lead is very essential to get something out within 10 weeks. It's very like short term, yeah, like sprint basically. Yeah, but I think we managed in the end, and it was a lot of fun. So yeah, if there's any questions or discussions, let me know. Thanks.
Nice. Very good. Nice presentation. Very good working demo. I think you guys can be very proud of yourself and what you have put down in the last 10 weeks. As you said, it wasn't an easy start, but you guys pulled through, and yeah, it's really cool to see it actually working already. So I'm very curious to see the final product with all the integrations from the other teams as well. That's super cool.
Yeah, same.
Thank you, guys. So questions. Let's see. Masum has a question.
Great work, by the way, guys. It's amazing to see this work. I just wanted to ask, is there, like, what is the overhead of using this application, you know, from a time perspective or CPU processes perspective?
I'm not sure what overhead means. I'm sorry.
But
like as in like, do you mean memory usage of the application, or
as in like, does it I was just wondering, I mean, it looks pretty fast anyway, and it looks very simple, so I'm pretty sure it doesn't use much CPU processes either. But I was just wondering, like, if, you know, if it can take up some CPU processing from the model inferencing or training part, I guess.
Oh, okay. So we didn't actually explicitly test this out, but like during development, I found a few times that if you load multiple files in at the same time, at some point it crashes because there's no CPU memory, like no capacity left. But besides that, everything was working smoothly. But I didn't actually measure anything explicitly, so I couldn't tell you more than this. Yeah.
Nice. Yeah, well, that makes sense.
So I can just add, like, I think the issue you might face, for example, is with loading many files, is the fact that the GUI itself is not smart yet in any way with the processing needs to do these type of tasks. But in the end, it's basically just forwarding like a call to whatever Python script you're running. So in that sense, it's quite light, I think.
Yeah, no, that makes
You know what I mean? Yeah, so a few classes and
right.
Yeah, I guess like a static application like this would have about no load on the CPU. It might, depending on how many libraries you use, it could have a memory load that is significant, but that would still be sub-gigabyte. But a static application like this should use about no additional CPU power if you simply connect it to a backend, which I guess is the case in this application. So that should be very low.
Oh, okay.
I don't know if it's possible, but you can.
Yes.
I think in like Task Manager, you can see how your CPU is performing. Like maybe you can run the application and see how it changes. But like, I think it's very low. Yeah, it doesn't use much.
Cool. Thanks everyone.
All right, Daniela.
Hi. First of all, thank you so much for all your efforts. The application looks really like simple and nice, just how it should be. So that's really great. I was wondering how the application deals with very, very large data sets. So we just imagine 6,000 24-hour files. Do you have to select each file separately, or can you just select all of them at once and load them into the application? And then also on the output side, will you get a separate output files, one for each sound file, or are you going to combine them into larger output files that have multiple 24-hour files combined?
Yeah, so for the output part, we're still imagining how we want to construct files for different input files, basically. Because I think, from what I understood, you want to be able to make selection tables from multiple audio files, correct? Right.
Mm-hmm.
Yeah. So right now it only constructs CSV files per input file, but we can modify this for the large data set. I mean, you can select an entire folder, for example, as input, and then you could click to analyze all files currently loaded in. How it would do with 6,000 files, I'm not sure at the moment. Because it would take much longer, of course, but I'm not sure how the constraints are right now, like if it actually would run on that many files. But I mean, we have some time to research this still, I think, because it is how it would be used in practice. Right? So
I think it looks very nice that you have, this file-specific output directly in the application. But for 6,000 files, which is what we generally handle when we run these detectors, it's not really necessary, I think. The most important thing is that we have a progress bar that tells us that the application is actually doing something and it's not stuck. And we can review the output just by looking at the output files in the end. So you could actually make it even simpler, if that helps in terms of handling the large data sets.
Maybe, so you have to be a little bit smarter. So there's a few things that just the framework and stuff makes you have to think about how to do large numbers of files. For example, you have to specify how many of the input elements you have in advance. So how would you even visualize 6,000 files? You can't, but you will need something like a page then, right? So maybe 100, and then skipping in the page to go through next pages and so on. So yeah, that's one part, and the other part you might run into is like performance issues with multi-threading and things. So yeah, short answer is not great yet, but it's been thought about a little.
All right, thank you. I'm happy to chat more.
That'd be great. Yeah, thanks.
All right, great job, guys. So for our final presentation, we had a team looking into the implementation on Edge.
Yeah, all right. Final team. I hope everyone is still awake. I hope my internet will not give some issues. If the connection issues arise somehow, maybe I'll just ask someone of the team to jump in and take it over. So last few weeks, the team that's been like actively working, even though maybe 1 minute before the presentation for some part of it, are these. Yeah, let me join everyone in thanking also the Elephant Listening Project for such an incredible, interesting challenge, and Fruit Punch, first time to participate. It's really been great. Yeah, like a bit of a crazy process, but very, yeah, lots of learning opportunities. Right, so the problem we were facing is that the current audio monitoring that's done by the Elephant Listening Project and their partners relies on retrieving the devices from the forest and doing the analysis with the model or by hand after the fact. That means that if you want to protect elephants by deploying rangers, you're never on time, I guess, to catch the poachers, or at least you never know in real time if they were there, and you also don't necessarily know in real time where the elephants are or what their behavior is. So the ultimate goal or the vision would be like a network of edge devices that each have a model, a trained model, and can process audio information at the site in real time, and then be connected to each other so that the signals can be sent to base camp via some process. However, there's many challenges to realize that. I think we'll definitely be much more in the proof of concept and like having lots of explorations done and report on them than some of the other parts of this challenge, which are more complete solutions. And we won't even touch things like networking or energy supply or so on. So the goal we set out to do is give a proof of concept for the detection model deployed on an NXP device, which we have hooked up in the Fruit Punch lab. And in the end, we landed on having two directions, basically, namely using Edge Impulse and TensorFlow Lite libraries and do straight TensorFlow Lite conversion of the model. What we didn't do is look into the NXP tool suite that also exists, partly because the documentation was quite horrible. And I guess one thing to argue that this is the right approach is that it means that your solution is not dependent just on the specific hardware provider. As many in the challenge, we also faced a few struggles. First of all, because everyone was working in parallel, we couldn't quite get from the get-go a model from the model exploration team, for example, that we could then investigate to do conversion or deployment on, and all the improvement or like the things like quantizing and things you need to do to have it deployed on the edge. To test the model, also, we weren't able to access the microphone, and it was quite struggle anyway to think about how to profile the performance on the device. All right, with that, so these will be the kind of two directions that we will present here, the Edge Impulse one and the TF Lite phase one. I'll give it to Timothy for the edge impulse part. And I also heard maybe a question raised by someone. I'm not sure if that's the case. All right. Okay, Timothy, can you take it over? I'll keep on sharing.
Yeah, thank you, Sebas, and hi everyone. So, yeah, so during the midterm presentation, we have already presented how we can deploy Edge Impulse model on the NXP board. So this model is basically this is this project built by me, and it uses keyword spotting. So I tried to deploy this on the NXP board, so directly from the Edge Impulse. So I used the CLI. So we have already presented on how we can directly deploy this the Edge Impulse model to the NXP board. And then, yeah, can you move a slide, please? Next slide, please. Yeah. So apart from that, apart from using the Edge Impulse CLI to test the model on the NXP board, we also have an option in Edge Impulse to export model in the different formats. So particularly for the NXP board, we need to export this model as the C++ library, since the NXP is a Linux-based system, and the C++ library can be deployed on most of the Linux-based platform. Next slide, please. And apart from in the previous slide, what I have shown is you can convert the Edge Impulse model to C++ library for the model which has been built using Edge Impulse itself. But suppose if you have built the model on somewhere else and not on the Edge Impulse platform. So Edge Impulse recently introduced a new feature called Bring Your Own Model. So using that also, we can first take our model to the Edge Impulse, and then we can quantize and convert that model to the C++ library for the target hardware. Next slide, please. And then I have tried to install the Edge Impulse Linux SDK on the NXP board. So I logged into the NXP board, which has been provided to us. And I tried to install the Edge Impulse Linux SDK. So these are the commands which I have used. And the library also, because our model is going to use the sound audio processing, so I have installed that library also. So once the model is deployed, so here is the screenshot in which you can see that the library has been the SDK has been successfully deployed on the NXP board. And once the SDK has been deployed, the next step would be is to take the exported model, which we have exported as the C++ library. We can take that model and unzip that model in the directory where the SDK has been installed, and then we can use the C++ source file. So the Edge Impulse already produces the inferencing code. But this C++ source file can also be used if you need to add some other custom code. For example, if you are building an edge device that run the inference and then immediately transfers the result to some cloud server. So this C++ source file can be utilized for that. So once the modification has been made, we can build the application using the command which is specified in this slide, and then the firmware is available for us. Okay. And Edge Impulse also provides the Eon tuner which we can use to quantize the model. So once the model is optimized, this model can be fit on most of the resource constraint devices. So this is how we can definitely use the Edge Impulse platform. So although I have installed the SDK on the NXP board, and because I couldn't access the microphone on the NXP board, so I couldn't test it. But I'm very sure that the model can execute successfully on this NXP board also. And I have tried and tested the similar thing on some other Linux based board. Thank you, sir.
All right, thank you so much, Timothy. Am I still audible? Did I switch off my mic?
Yep.
Right, yes, all right. Yeah, so then the second part, or the second attempt, was to basically base ourselves on the first or the second workshop that we had in the beginning of the challenge, which was by the Rainforests Connection project. And they use YAMNet from Google Research for bird song detection in their case. And so to have some model that we could play around with and get our hands dirty, we tried to use this one and adapt it to the rumble and gunshot detection as well. So this was definitely a collaborative effort with much work in the last few weeks of everyone. And I'll try to highlight a few of the findings. So first of all, it appears that the conversion to a TF-Lite model is a little bit model specific. So it's very hard to give some general advice on how these things go, because you're dependent on the operations that are used. So I'll just give this for YAMNet. What turned out to be problematic for applying it via TF-Lite is basically two parts. So the spectrogram conversion that was there in YAMNet made use of some operations that cannot easily be converted, and the waveform input needs to be of a fixed size, different from the standard YAMNet implementation that takes audio waveforms as an input, because TF-Lite cannot handle with this undetermined input size. But as you'll see, that's actually only in the part of the model that is used for inference and is not necessary for the training of the model. So in principle, you can take the trained YAMNet and stick these two things in front, and it should be giving you a model that is all right for TF-Lite conversion. Now, what we wanted to show today, I guess, was a full POC if it would have worked out before the challenge deadline. But the problem was that we had to, or we ended up trying to solve a lot of the problems that all the other teams also were facing, I guess, about the data set, about every part of the pipeline, because we were doing a full model training. So it's not complete, but here are the parts that sort of work. So we have a training and TF-Lite conversion shown on the local devices. The TF-Lite model was deployed on the NXP device, and then we did some inference with use of the tensor processing unit that was there, or the neural processing unit on the chip. And the idea was to also augment it kind of with some evaluation, so having an idea of how good the model is, both on the chip and the local environment. And a way which would have been nice is to use weights and biases logging, in particular to check the behavior on the chip, but that didn't quite work out yet. All right, just to kind of show that at least give you a screenshot of that should convince you that there was a custom YAMNet deployed on the chip. So here are the labels: gunshot background, rumble, but it's a fake model. This hasn't been trained on anything. However, it's nice to see that it does use MPU and CPU and splits operations that are not suitable for the MPU, delegates it to the CPU. Now, this was very fresh from the press, just before the meeting. Some training results, so we hope to kind of wrap this up in the next week when we collect the code and write the report and stuff. So conclusions, well, these two avenues for deploying the model on the chip are at least there. They are independent of the NXP device, but seem also to work on the NXP device. It may be that the Edge Impulse one is more efficient because it can use natively compiled C++ code, but you have to work with C++ to do kind of, as Timothy explained, whatever you want to do other than the pure model inference. So TF Lite is also very flexible, and you can use Python code to do other things around it. But yeah, it may not be optimal. So with that, let me conclude and see if there are any questions. I hope it didn't take too long.
All right, thank you. Good presentation.
Yeah, I'm impressed that in the end you got like the full pipeline working, right? There were some troubles getting the NPU working as well, but now you have full pipeline that also gets all the data from S3 that's able to run on the NPU. That's quite impressive. In the end, you only tested it with one model, of course. It would have been interesting to see how the NPU performed compared to the CPU within the NXP device, but that's mostly just interesting, I guess, in this case, not working towards the goals of the project for now, which is, of course, getting this stuff done in real time. You mentioned that you were not able to connect or to use the microphone on the NXP device. I did have one connected. I'm not sure what happened there. Like, but
maybe I should rephrase. Like, we didn't know what to test for. I mean, in the end, so one idea was to stream the files from the S3, and then check the model performance on the files because it would actually have some detections. We didn't try at all to connect to whatever background noise there was on the microphone. That would have been interesting. But.
And what do you think, because you did, of course, then test the inference time, etc., of these models, what do you think of the feasibility of using this device to do live inference?
Yeah. So, well, there's the advertisement of them, which is, I think, we looked this up. Like, it's a frame rate of what's it like okay, I forgot the numbers. I should look them up here. But the NPU in principle should be capable of like a frame rate, if I'm not mistaken, of like 30 kilohertz or something. Analysis of spectrograms. Probably also some high sampling rate spectrum. So it's like the device is basically made for situations in cities or whatever, right? Where I think in this application, actually, you were okay with actually quite low sampling rate and also a frame rate of analysis. So I don't think the bottleneck would be the inference time for this to work, which is good. And also, in the beginning of the challenge, we talked about like seeing whether other parts of the hardware would be good for doing the pre-processing, because there's some audio processing unit, if I'm not mistaken. But I think with the like kind of 5-watt power and the use of the NPU, it's probably very feasible to just put the pre-processing or the spectrogram generation within the model, and yeah, and use also the fact that you can then probably also delegate it to the NPU.
Okay,
but I think
so
maybe yeah, maybe Jaka or someone else has, or Juan has other things to add. So that's...
No, but that sounds good. So these NXP machines will be very usable for doing this live inference here as well. And does the same hold for Edge Impulse? I think mostly Timothy worked on that, like using Edge Impulse for deployment. I did get it working on the NXP device using a microphone already, like I tested that before we started the challenge. If you could comment on that,
Yeah,
Timothy, about the
so-
feasibility of using that as part of the pipeline.
Yeah, I think so. The idea is to build a device which can detect the voice in real time and do the inferencing. So the edge impulse could be one of the best option for building such kind of devices and building such kind of models. And for my other projects like the keyword spotting project, so I have seen the inferencing time is somewhere around few milliseconds on the other devices, but I haven't tried it on the NXP. So I think the result would be quite similar.
Okay, very good to hear. And what's also convenient, if I hear you right now, also when you mentioned being able to do quantization as part of the edge impulse pipeline, which of course takes quite a lot of effort if you do that manually.
Yes. Yeah.
Very
So
cool.
it's the edge impulse has
thanks.
the built-in tool. Yeah. So
All right. Thank you, guys. Really cool to see all the progress you've made.
I think there is.
You'll, yeah.
Sorry, I think there is one comment in from David in the chat box.
Yeah, the native support for the NXP NPU is coming, so that's good to hear. So next iterations we'll be able to fully support that.
Thank you all for working on this challenge. I think you guys all did unbelievably good, but I want to give Daniela the word for give some final notes.
Thank you, Dorian. I have only words of thanks to you guys. It's I can't thank Dorian and Sakurina to coordinate this and bringing you all together. And I think you guys have all worked so hard. And I know that most of you are working full time besides doing this challenge. So this was a lot of extra effort for you. So I really, really appreciate it. And I'm very, very excited to start playing around with the products that come out of this here. Thanks so much.
All right. Yeah, we'll make sure that the product is finished by next week and delivered on in your email. Thanks everyone for being here, and I'll speak to you all soon.